Take a look at this messy, jagged wave. It could be a piece of music, a radio signal, or the beating of a heart. It looks chaotic and impossible to pin down. And yet, more than 200 years ago, a beautiful mathematical idea was born. The claim that any tangled signal in the world, no matter how complex, can be broken down into a sum of the simplest possible waves. That idea is called the Fourier transform, and it is one of the most powerful tools humanity has ever devised. The story begins in 1807, when a French mathematician named Joseph Fourier was wrestling with a seemingly ordinary problem, describing how heat spreads through a metal bar. To solve it, he made a claim so bold that it left the mathematicians of his day in disbelief. That every function, every curve, could be rewritten as a sum of sine and cosine waves. At first, nobody believed him, but in time, his idea proved not only correct, but far more far-reaching than even Fourier himself could have imagined. To understand Fourier, let us first meet its basic building block, the sine wave. A sine wave is described by just two numbers: its frequency, which tells you how fast it oscillates, and its amplitude, which tells you how tall it is. The magic begins when we start adding sine waves together. With just one wave, we get a simple curve. But add a second, a third, and then dozens of waves with different frequencies and amplitudes, and an entirely new shape emerges. Here, from nothing but smooth, rounded curves, we build a sharp, square wave. The more waves we add, the more exact the shape becomes. This is the core intuition, that everything is built out of sine waves. Now let's look more closely at the formula behind this game of stacking waves. It's called the Fourier series. Any periodic signal can be written as a constant, a sub-zero, plus a sum of infinitely many waves, where the nth wave is a sub n times cosine of nx, plus b sub n times sine of nx. It sounds tangled, but the meaning is simple. Each pair of coefficients, a sub n and b sub n, is just the volume knob for the nth wave. The larger the coefficient, the more that wave contributes to the final shape. Take the square wave from a moment ago. Its volume knobs are 4 over pi. Then 4 over 3 pi. Then 4 over 5 pi. Shrinking steadily. So how do we find these coefficients? The formula hands us a beautiful detector. To find out how much of the wave cosine nx is present in a signal, we simply multiply the signal by that very wave, and take the average over one period. If the signal contains that wave, the products resonate and add up to a non-zero number. If it does not, everything cancels out cleanly, and the average is exactly zero. Multiply, then average. That's all it takes. That is how the Fourier series digs out every single building block of any periodic signal. To see clearly how this machine works, let's compute the Fourier series by hand for a concrete example. The very square wave we just built. We define it simply. In the first half of the period it equals +1. And in the second half it equals -1. Repeating forever. Step 1. Notice the symmetry. This square wave is an odd function, meaning if you flip it through the origin, it lands exactly on the mirror image of itself. And an odd function cannot contain any cosine wave, because cosine is even, so all the a sub n coefficients are 0. And we only need to find the b sub n coefficients of the sine waves. Step 2. Apply the detector. The coefficient b sub n equals 2 over the period, times the integral of the signal times sine nx. Using the symmetry, we only need to integrate over the first half period, where the signal equals +1. Then b sub n equals 2 over pi, times the integral from 0 to pi of sine nx, dx. Step 3. Evaluate the integral. The antiderivative of sine nx is minus cosine nx over n. Plugging in the upper and lower limits, we get b sub n equals 2 over pi, times 1 minus cosine of n pi, all divided by n. Step 4. And here is the loveliest part. Cosine of n pi is always equal to -1 to the n. If n is even, it equals 1, so 1 minus 1 is 0. And the whole coefficient vanishes. But if n is odd, it equals -1, so 1 minus -1 is 2. And b sub n equals 4 over n pi. Putting it all together, we get the final result. The square wave equals 4 over pi, times sine x, plus sine 3x over 3, plus sine 5x over 5, And so on forever. And look, those are exactly the volume knobs 4 over pi, 4 over 3 pi, 4 over 5 pi that we met earlier. From a definition just a few lines long. With exactly two operations, a multiply and an integral. We derived by hand the exact formula of an entire signal. If every signal is a sum of sine waves, a natural question arises. Given a signal, how do we know which waves it is made of? This is exactly the job of the Fourier transform. Think of it like a prism. When white light passes through a prism, it splits into the 7 colors of the rainbow, revealing all the hidden component colors within. The Fourier transform does exactly the same thing. But with signals, it takes in a wave over time, and hands back a full list of frequencies, along with how strong each one is. We call this going from the time domain to the frequency domain. And that list of frequencies is the signal's unique fingerprint. But how can a formula actually detect these hidden frequencies? The mechanism is surprisingly clever. We take the signal and wind it around a circle, at a rotation speed of our choosing. Most of the time, when the rotation speed matches nothing in particular, the signal spreads evenly around the circle, and its center of mass sits right at the origin. But at the exact moment the rotation speed lines up with a frequency truly present in the signal, everything suddenly clusters to one side, and the center of mass leaps far away from the origin. That leap is the signal saying, a frequency has been found. Picture it like tuning the dial on an old radio. The instant you hit the right frequency of a station, its sound rings out clearly from the sea of noise. The Fourier transform, in essence, tries every frequency at once, to see which one truly resonates with the signal. This whole beautiful idea is captured in a single integral, whose core ingredient is the complex exponential, the thing that describes that circular winding motion precisely. You might wonder why the formula needs complex and imaginary numbers, instead of ordinary ones. The answer is that a complex number is the most natural way to describe a spinning arrow. It tells you both how long the arrow is, and which direction it points at every instant. And thanks to complex numbers, the Fourier transform gains a special power. It can distinguish waves spinning clockwise from those spinning counterclockwise, something mathematicians call, intriguingly, a negative frequency. By now we have everything we need to dissect the Fourier transform formula, symbol by symbol. But first, we need one connecting link. In the Fourier series we used sine and cosine separately, while here a complex exponential appears instead. The bridge between them is Euler's beautiful formula, which says that cosine theta plus I times sine theta equals e to the I theta. In other words, a unit-length arrow rotated by an angle theta packs both the cosine wave and the sine wave into a single symbol. That is exactly why the Fourier formula can be so compact. Now, written out in full, it reads, f hat of omega equals the integral of f of t times e to the minus 2 pi I omega t dt. Let's read it from the inside out. The term e to the minus 2 pi I omega t is an arrow spinning steadily at omega turns per second. Precisely the winding motion around the circle we just saw. Multiplying it by the signal f of t means winding our signal onto that circle. Where the signal is large it reaches far out. Where it is small it pulls in close. The integral over t is just the sum of all the points along that wound-up curve. And summing all the points is nothing other than finding their center of mass. And the final result, f hat of omega, tells us how far the center of mass flings out at this rotation speed omega. That is, how strongly the frequency omega is present in the signal. The reverse direction is just as beautiful. Once we hold the full list of every frequency, we simply rebuild all those spinning arrows and add them back together. This time spinning the other way. That is, flipping the sign in the exponent from minus to plus. And they reconstruct the original signal exactly. That is the inverse Fourier transform, the key to travel from the frequency domain back to the time domain. And it is precisely this that lets an audio engineer erase a spike of noise and then rebuild the signal as before. Or lets an MRI machine reconstruct an image of the body from the frequency data it collects. There and back, analysis and synthesis, two directions of the very same transform. One last subtle point, the Fourier series is only for periodic signals, whose frequencies are discrete, whole number multiples of a fundamental. So what about a signal that is not periodic? Picture it as a periodic signal whose period has been stretched out to infinity. As the period grows longer, the discrete frequency lines crowd closer and closer together. And in the limit they merge into a continuous band. The summation sign then becomes an integral sign. And the Fourier series officially becomes the Fourier transform. The version meant for every signal in the world. One formula, 4 symbols, and the entire frequency detecting machine sits neatly inside. That was an example for a periodic signal. Now let's compute by hand the Fourier transform of a classic non-periodic signal, a single lone rectangular pulse. We define it as 1 on the interval from -a to a. And 0 everywhere else, never repeating. Step 1. Plug it into the formula. Since the signal is 0 outside the pulse, the integral from -infinity to +infinity shrinks down to just the integral from -a to of e to the -2 pi I omega t dt. Step 2. Evaluate the integral. The antiderivative of e to the -2 pi I omega t is itself divided by -2 pi I omega. Substituting the two limits a and -a, we get e to the -2 pi I omega a minus e to the +2 pi I omega a all over -2 pi I omega. Step 3. This is where Euler's formula steps in. Recall that e to the I theta minus e to the minus I theta equals 2I times sine theta. Applied to the numerator, it becomes -2I times sine of 2 pi omega a. The -2I in the numerator and in the denominator cancel neatly. And we arrive at a surprisingly beautiful final result. Sine of 2 pi omega a divided by pi omega. This is the famous sinc function. Instead of just a few sharp spikes, its spectrum is a continuous curve. One large hump in the center, with smaller and smaller ripples out to each side. And a deep truth is revealed: the narrower the pulse in time, that is, the smaller a is, the wider the sinc spreads out in frequency. And vice versa. To be compact in time forces you to spread out in frequency. That is the very origin of the famous uncertainty principle in quantum physics. Which, in the end, is really just the Fourier transform. And when we let these waves live in the complex plane, something spectacular happens. Each frequency becomes a vector spinning at a steady rate. Chain many of these vectors tip to tail, each turning at its own speed. And the very last tip can trace out almost any shape you like. From a heart, to a letter, to an entire intricate portrait. This is the complex Fourier series. And it is the most beautiful demonstration of the power of adding up waves. But there is a problem. That elegant integral formula integrates over continuous time, running from one infinity to the other. And a computer simply cannot handle the infinite and the continuous. It only works with discrete, finite numbers. So in practice, computers use a discrete version, called the discrete Fourier transform, or DFT for short. The idea is very intuitive. Instead of an entire continuous signal, we sample it at n evenly spaced points, giving a sequence of n numbers. The DFT turns this sequence of n numbers in time into exactly n numbers in frequency. Each frequency value, the kth1, is computed by taking a sum, no longer an integral, of each sample times that same familiar spinning arrow. E to the imaginary power. The essence is exactly as before. Multiply by the spinning arrow. And add it all up. Only now, everything is discrete and finite. And it is precisely this DFT with its n data points that the FFT algorithm coming up next will speed up, cutting the number of operations from n squared down to about n times log n. Now, there is a very practical problem. In theory, Fourier's formula is elegant, but if you ask a computer to compute it directly on a signal with millions of data points, the number of operations grows with the square of the size, becoming so enormous that it is simply infeasible. For a long time, the Fourier transform remained a tool that lived only on paper. The turning point came in 1965, when two scientists, Cooley and Tukey, published a magical algorithm called the fast Fourier transform, or FFT for short. By cleverly splitting the big problem into smaller ones and reusing repeated calculations, they slashed the number of operations from the square of the size down to roughly n times log n. It sounds abstract, but the consequences are immense. A computation that would have taken hours now happens in the blink of an eye. It is this FFT algorithm, not the original formula, that quietly runs inside every phone, every speaker, and every screen around you. So how exactly does the FFT break the problem down? Let's take an example with 8 data points. The secret of Cooley and Tukey lies in one simple observation: split the 8 points into 2 groups. The points at even positions, and the points at odd positions. The magical thing is that the Fourier transform of all 8 points can be assembled from just 2 smaller transforms. One for the 4 even points, and one for the 4 odd points. And here is where the saving comes from. The result of each small transform gets reused twice, for both the upper and the lower halves of the spectrum, differing only by a single plus or minus sign. This combining operation is called a butterfly, because its diagram looks just like a pair of butterfly wings. And the 4 points split again into 2 plus 2, and 2 splits into 1 plus 1. Having like this, we get log base 2 of 8 in total. That is, 3 stages. Each stage costs only about 8 operations. So the total is just 8 times 3, instead of the 8 times 8 of direct computation. With 8 points the difference is still small. But with a million points, n squared is 10 to the 12th, while n times log n is only about 20 million. Roughly 50,000 times faster. All thanks to one single trick: split by even and odd. Then reuse the results. Now for the applications that change the world. First, sound. Every time you adjust the bass or the treble on a speaker, you are really turning specific groups of frequencies up or down. And that is Fourier at work. When a recording is plagued by an annoying hum or hiss, an audio engineer simply transforms it into the frequency domain, finds the exact offending frequency, deletes it, and transforms back. Just like that, the noise vanishes. Even the MP3 format you listen to every day relies on Fourier, by discarding the frequencies the human ear can barely hear, shrinking the file size many times over. The second application lives inside every photo on your phone. An image can also be seen as a signal, only spread across 2 dimensions instead of 1. When we apply the Fourier transform to an image, the large, smooth patches of color end up in the low frequencies, while the tiny details and sharp edges live in the high frequencies. The secret of the JPEG format is that the human eye is not very sensitive to those high-frequency details, so we can boldly throw most of them away. The result is an image that looks almost identical to the original, but with a dramatically smaller file size. In practice, to do this efficiently, JPEG does not transform the whole image at once. It splits it into countless little 8 by 8 pixel blocks, and applies a version of the Fourier transform to each one, keeping only the few most important numbers and rounding away the rest. Multiply that little trick across the millions of images captured and sent every second across the planet, and you will see just how much data Fourier is quietly saving. But the story does not stop there. In medicine, MRI machines do not actually photograph your body directly. They collect data in the frequency domain, then use the Fourier transform to reconstruct detailed images of the organs inside. Without Fourier, modern medical imaging could hardly exist. Have you ever wondered how an app like Shazam can hear just a few seconds and instantly name the song? The secret is the same. It turns the audio into a map of frequencies, creating a unique fingerprint for the song, then matches it against millions of fingerprints in its database. Geologists use Fourier to analyze earthquakes, separating vibration components to predict quakes and to hunt for oil buried deep underground. And in a fitting twist, the very problem Joseph Fourier first studied, the flow of heat, still relies on his formula today. In simulating weather, fluids, and countless physical phenomena, from transmitting phone and Wi-Fi signals, to analyzing the light of distant stars to learn what elements they are made of. All of it carries Fourier's fingerprint. So what is the most beautiful thing here? It is that with a single idea, that everything is a sum of waves, we can reach into music, images, medicine, astronomy, and countless other fields. A formula that seems dry and abstract turns out to be a master key, letting humanity see through to the hidden nature of every signal in the universe. And deeper still, Fourier reveals a truly beautiful truth, that time and frequency are just 2 different ways of looking at the very same reality. The same signal, viewed through time, is a moving wave, viewed through frequency, it becomes a chord of many notes. The Fourier transform is the bridge that lets us travel freely between those two worlds, anytime we wish. That is the timeless beauty of the Fourier transform. If you found this video interesting, do not forget to leave a like and subscribe, so we can explore more wonderful mathematical ideas together.